Thanks, Cynthia. Thank you, everyone. So I'm going to talk about what I call dusting for fingerprints in private data, and let me give you just a very high-level summary of the points I want to make in the talk. So first of all, what I'm going to do is I'm going to talk about something called tracing attacks. So this is a model of attack that's very tailored to finding privacy breaches in aggregated statistical information. So at the very beginning, Cynthia introduced the concept of re-identification and quickly put it aside. And I'm going to talk about what sorts of privacy risks we're worried about in settings like the ones we've talked about, where we're only releasing some kind of statistics about the data set. And as you can probably imagine, this is going to be a counterpoint to the two excellent talks given by Guy and Kunal, who presented the wonderful things you can do with differential privacy. But of course, despite all the power of differential privacy, there are limits. And I'm going to talk about when those limits are tight. And in particular, I'm going to talk about the case of high-dimensional data sets where those limits seem to be tight, or the types of algorithms they presented seem to be close to the best we could possibly hope for. And even though I'm often introduced as like the Grinch who stole differential privacy, I want to put this in a positive light. What I want to say is that the attacks I'm going to show you and the results that I'm going to state and give a little taste of the proofs of show that some of the differentially private algorithms you've seen, in particularly the composition theorems that Guy talked about, are actually going to basically match the limits that these attacks are going to impose. And that's actually a good thing for privacy in a sense. It's not that we want there to be limits, but it's actually a very good thing, I think, that we have this very strong formal notion of privacy. And in some sense, it gives us everything that we could hope for if we at least want to prevent these attacks. So I think that actually makes our lives easier in some sense, that it gives a very crisp picture of what's possible, at least for one setting that I'm going to talk about. Okay, so even though we put it aside, I want to start by just putting a little bit of context around different types of privacy attacks that people have referred to. So the most common are re-identification attacks. These are essentially attacks on data sets in the one-man, one-row model, where you take a data set and you anonymize it in some way, and an attacker can come along and re-identify that data. So you give out some data set like this, where each row is a person's data. Each column in this example is whether a person liked a given movie. This is a classic example of a re-identification attack due to Narayanan and Shmatakov. And then you get some sort of public information that maybe wasn't anticipated when this data set was released. And by combining them, the attacker can actually re-identify the data set and learn about individuals. And this is basically a paradigm that's deservedly come under a lot of assaults. So there's a nice statement from the PCAST report on big data and privacy that says anonymization is increasingly easily defeated by the very techniques that are being developed for many legitimate applications of big data. So this sort of model just doesn't work in high-dimensional data. The data is too big, it's too diverse to have any hope of anonymizing the data while preserving any utility. And so Cynthia puts it much more succinctly that de-identified data isn't. So moving beyond re-identification might give one the impression that if I just release some kind of aggregated statistics where there is no possibility of re-identification, that you're automatically safe. But this viewpoint was also upended by a beautiful, influential work of Dinur and Nissim from 2003, who showed that even if I just give you statistical information about the data set, but I give you too much statistical information and it's too accurate, then the attacker can reconstruct essentially the entire data set. So if I take this data set and I release some kind of statistics, like how many people like certain movies, what are good ways of clustering the movies, just some kind of aggregated statistical information, even then an attacker can reconstruct this data set and compromise privacy to a large extent. So these are very powerful and elegant attacks, but what I want to talk about is a kind of attack on aggregated statistics that's much more flexible and actually we've seen occur in the real world. And these are what we call tracing attacks. And in particular, there was this really stunning results by Homer et al. In 2008, where what they showed is that if I take a genomic data set and I give you only frequencies of certain genes or alleles in the data set, so the specifics of genomics are not important here, So I do something like this. I have a data set that consists of, say, sick people and a control group, and I publish just aggregated genomic information for the two populations. Then an attacker who has information about one individual but doesn't know which of the two sets that individual is in can actually detect the presence of that individual in one of these two data sets and thereby learn sensitive information. So this happened in practice. It led to policy changes at the NIH. And what's really shocking about this is that sensitive information about an individual was leaked even though nobody released any personally identifiable information. In fact, nobody released any information that was obviously specific to an individual in any way. So no one was re-identified, and yet a real privacy breach occurred with real consequences. So this is the kind of attack that I'm going to talk about today. I'm really only going to focus on this model. And the way that I would summarize the conclusion of this result is that individual-specific data somehow leaves a fingerprint even in these aggregated statistical data releases, and this fingerprint can be detected. It can be dusted for and traced back to an individual. And I'm going to talk about a few different tracing attacks in the course of this work. I'm going to describe sort of a formalization of the Homer et al. Attack. But I'm actually mostly going to focus on something that we call robust tracing attacks. So this was done in a joint work with Cynthia, Thomas Steinke, Adam Smith, and Salil Vadan a year or two ago. And what I'm going to show you is that there's a way to do these kinds of tracing attacks that's extremely robust to noise in the release statistics. So even if you try to somehow remove this fingerprint by perturbing the data in a very significant way, even a deliberate way designed to achieve privacy, it will still be detectable. And also, our attack is going to work under very mild assumptions, so it's not going to require very rich sources of external information for the attacker. And just to give you a hint of where the name comes from, the attack was sort of inspired, and its analysis was inspired by a very cool combinatorial object called a fingerprinting code, which was introduced by Bonnet and Shaw in the 90s, and then there's a very beautiful construction of Tardosh, and in joint work with Salil Vadan and Mark Bunn, who's somewhere around, we showed that it was connected to privacy. So this is the source of the fingerprint analogy. But the upshot of the result I'm going to tell you is that, at least in this one setting, it shows that differential privacy comes at very little cost beyond the limits that are imposed by these attacks. So these attacks are really going to work right up to the point where the utility of the release statistics is achievable with differential privacy. There's going to be almost no gap. And I should say, so give me a roadmap, but I want to say, please feel free to stop me in the middle for questions. Some of the kind of, the way we model things and the way that we analyze things requires some sort of time to grok, and so I'd be happy to take questions and address questions midstream. So first, what I'm going to do is I'm going to give you a model for tracing attacks. And when I say model, what I'm going to do is first I'm going to introduce a very simple problem, which is essentially the problem of releasing many arbitrary counting queries that both Guy and Kunal have referred to. And then I'm going to describe an attack in terms of what the attacker is trying to do, what they have access to, and give you basically a way to formalize what a tracing attack is. And then I'm going to spend a fair amount of time on statements and describing the attack. And I'm also going to give you demonstrations. So there's a good chance that I'm like the most theoretically minded researcher in the room. And yet I'm going to have actual experiments for the first time in my life. So this is a very exciting moment for me. I'm glad you are all here to share it with me. So I'm going to give you an actual demonstration of the tightness of differential privacy. So this claim I keep making that differential privacy comes almost for free beyond the limits imposed by the attacks, I will actually demonstrate. And then I'll talk at the very end about an extension we're working on about sort of selecting from many statistics in selecting a small number of variables out of a very high dimensional data set. Okay, good. So the star of our show is this data set. It is a binary matrix with n rows and d columns. And as we often do in differential privacy, one row is one person. one column is one attribute, okay? And I want you, due to limitations of space, I've drawn it only slightly short and fat, but I want you to think of this as a very high-dimensional data set. So really, it would be like very short and very fat. And the first thing you might think to release about this data set, pretty much the first thing you can imagine, is its mean. Okay, this is pretty much the most basic type of statistics you'd want to know about this data set. Just the mean, the average of all the rows. All right, and as we know, if we want to achieve differential privacy, or really any measure of privacy, we're going to have to perturb the mean in some way. And of course, we want to understand how much we have to perturb it. But so I'll add a new actor to the cast, which is this noisy mean. So instead of releasing this mean, you take the data set and you release some noisy mean that we hope approximates the true mean well. And we want to basically understand the interplay of how well we can preserve the privacy for each individual in the data set, each row of X, and how much noise we have to add to this Q hat. Right? So these are the main kind of notational features that are going to come up throughout the talk. A data set X of dimension D, its mean Q, and a noisy mean Q hat. So what can you do with this mean? Right? It doesn't seem like you can learn a lot of individual specific information just from the mean, especially when n is very large. So let's think about something that the attacker might try to do. So here's a model that we call a tracing attack. And as usual, so we'll have the data set and some noisy mean. So the attacker gets this noisy mean. And the attacker also gets the data of some target individual T. So this is some person in the world. I know a lot about this person, but I don't know if they're in the data set or not. Right? And as I told you in this example of this Homer et al. Case on genomic data sets, even knowing whether or not the target is in the data set can actually be sensitive information. So there really might be multiple data sets that connote certain features, and so learning if this person is in the data set is itself a privacy breach. Okay, so the attacker gets the noisy mean and the target individual. And now I'm going to augment the model a little bit by assuming that the data set actually comes from some probability distribution. All right, so just imagine that every row in this data set is an independent draw from some probability distribution. And we're going to assume that it's a product distribution for today, but at least as far as the model is concerned, it can be just from some family of distributions. All right, and the attacker is going to get, in addition to the target and the noisy mean, the attacker is going to get the mean of this distribution. So the attacker, in some sense, knows the environment in which the attack is operating. All right, so these are the three things the attacker gets. And now the attacker's goal is to determine, is this target individual a random member of this data set? So someone just drawn from one of the n rows in this data set? Or is the target individual a random member of this population? Someone who had nothing to do with being in this data set, just a random person. Okay, and I'm going to refer to these two cases as in and out. So this will come up a lot. There's going to be the in case where T is randomly sampled from the data set, and the out case where T is randomly sampled from the population independent of the data set. And I just want to say again, notice that in this model, the attacker does not get anything to re-identify. There's no possibility of a re-identification attack because the attacker only sees these aggregated statistics. Okay, so this is the model for a tracing attack. Is there any questions? Yeah? Yes, the exact same features. Now, of course, if he had information on a subset of features, right, if there were more features in the data set, we could throw some out. But yes, for the model, we'll just assume that the data set and the target individual are from the same domain. Okay, good. So let's see what we can do, like what sorts of tracing attacks are possible. So the attack of Homer et al. was an empirical attack, but it was formalized in a model by Sankara-Raman et al. And what they basically showed is that the attack gives you the following. So it says that if I give the attacker the target's data, the mean of the population, and the exact mean Q, so none of this noise, the attacker just gets the exact mean of the data set Q, then if the dimension of the data is bigger than n, if this database is wide, wider than it is tall, then the attacker can determine if the target T is in the data set with high probability. And there's a small caveat, the population P has to be not too biased, but this is a technical condition. All right, so this is in some sense kind of a ratification of the statement that both Guy and Kunal made, which is that if you want to release n queries on a sensitive data set, you have to add significant noise. Now, I know that I told you that you need the exact mean. I'll say in a second that you can tolerate some noise. But you can basically think of this result as saying that you have to add noise on the order of the sampling error if you want to answer n queries on the data set. And what I mean by that is, in this model, there's some noise already in the data, right? The thing you're after is not really Q, the mean of the data set. The thing you're probably after is actually P, the mean of the population. That's probably the object of more interest to you if you're a scientist. Maybe not if you're an attacker, but if you're a legitimate scientist, that's probably what you care about. And if I have a data set of size n sampled from this population, then on average, over the coordinates of the mean, the error is going to be about 1 over square root n. Okay, and so you can think of the attack I just showed you as a statement that says, if you're trying to answer more than n queries, or even just compute the mean of an n-dimensional data set, the amount of error you need to add has to be on the same order as the sampling error. Okay, and that's because this attack is robust to a small amount of noise. It can tolerate noise in the mean on the order of 1 over root n. Okay, so that's something. So we know that if we want to answer queries with error proportional to or dominated by the sampling error, we can only answer n queries. But what's really interesting is what happens if we are willing to tolerate some error? So we are willing to pay something for privacy. And we're willing to tolerate more error than the sampling error, but we still need to get some non-trivial approximation to the mean of the data set. So I'm going to tell you about what I'm calling the robust tracing attack, which can handle that error. But let me start by sort of introducing, let me just go over like what are the sorts of things that are now allowable if I'm worried about noisy means. So let's recall from Guy's talk, and I guess also from Kunal's talk, that a pretty good way to achieve differential privacy, or I guess more accurately, epsilon delta differential privacy, or epsilon concentrated differential privacy, is to add Gaussian noise. And Guy went over this in a lot of detail, but the upshot is that if you want to release the mean with if you want to release the mean of this data set with differential privacy, the amount of noise you have to add is about square root of the dimension d over n. Okay, and notice that this noise, as Guy said, is smaller than the sampling error when d is smaller than n. When d is about n, this kind of matches the sampling error. But even when d is as big as about n squared, you're going to get some non-trivial approximation to the mean. All right, so in the attack I described, I said we can trace successfully when you get the exact mean of the data set with d roughly equal to n. But if I want to tolerate a lot of noise, I can't possibly have that guarantee because differential privacy will prevent tracing attacks. So we're going to have to weaken our goal a little bit and consider even higher dimensional data sets. And of course, another thing that you can think about is subsampling the data set. Now, what I mean is, you just throw out most of the rows of the data set and you compute the exact mean of the rows you keep. So this is not a differentially private algorithm, right? We don't think of this as differentially private because some people in the data set are going to lose all privacy. Okay, and in some, philosophically, you might be happy with this. I don't think this is a good solution for privacy. But this is something we have to consider. And the reason we have to consider it is because in the attack I showed you, I said we can basically tell whether any person is in the data set or out of the data set. That's going to be hopeless now because if I'm allowing you to add some significant noise to your data set, then I have to consider the possibility that you're actually throwing out the vast majority of the data set. So in fact, if you only want accuracy that is sort of barely non-trivial, like you just want to be able to distinguish attributes that are kind of all negative ones from attributes that are all positive ones, you only need to sample like a single or like constant number of people. So this is going to severely limit what we can do. And in some sense, what our result is going to show is that these are really the only things we have to worry about. That basically the sort of only two mechanisms that can really constrain what a tracing attack can do are throwing out large chunks of the data and accepting the price inaccuracy, or adding Gaussian noise. So I want you to think of the next result as basically saying that these are like the two extreme things you can try to do to prevent tracing attacks. One of them is very nice and achieves differential privacy. The other I don't think of as very nice for privacy, but is a legitimate thing you could do. And so our result is that if the attacker is given the same target's data, same as before, and now some extremely noisy mean of the data set, so any approximation to the mean of the data set such that the average error over coordinates is about 1/10. It's not really crucial what the constant is. The point is that the answers range between -1 and +1, so this is like the minimal thing you could possibly have and say you're getting an approximation to the mean. Okay, and there's one more modification, which is that the attacker now only needs one random sample from the population. So I'm not even going to require the attacker to know the population from which the data set was drawn. The attacker just needs like one independent random person of roughly the same type as the people in the data set. And under these assumptions, if the data set is about n squared dimensional, if d is bigger than n squared, then the attacker will be able to trace at least one person in the data set. Okay, so what I mean is that there will be at least one person in the data set where the attacker says, yes, that person is in this data set. Anybody who is a random member of the population, the attacker is very, very overwhelmingly likely to say, no, that person is not in the data set. Okay, so like I said, in some sense this is weaker. We only trace one person in the data set, and we require that the dimension be bigger than n squared. But these conditions are somewhat necessary, and in exchange we basically get to say that tracing attacks are essentially impossible to defeat without adding differential privacy. These are basically the guarantees you would get. These basically are right up until the guarantees you would get from differential privacy. Right, so one thing I want to do is I want to give sort of an interpolation between the two attacks I described. So these are like two extreme points, the case where you get extremely large noise, and what I showed you before, the case where you get noise that's so small that it's dominated by the sampling error already in your data set. And I just want to quickly say that there's really a whole spectrum of trade-offs. So for example, if you kind of reparameterize the problem and you say you're willing to tolerate alpha error on each coordinate, then you can achieve that by adding Gaussian noise with standard deviation alpha. And adding that much noise will be differentially private as long as d is smaller than about alpha squared n squared. Right? So you don't need to be able to figure out exactly why this is true, but it's just it follows somewhat from Guy and Kunal's talks. Okay, so if we want more accurate statistics, we can hope to trace with lower dimensional data and smoothly interpolate between the two extremes. And similarly, if you wanted alpha noise in your data, one way to achieve it is by subsampling more than a few people, by sampling about 1 over alpha squared people from your data set. And this is, of course, going to make it impossible to say anything about the other n minus 1 over alpha squared people, but under this scheme, about 1 over alpha squared people will lose everything. And we can basically give a smooth quantitative trade-off in all these parameters. So if you give me the mean with error about alpha on each coordinate, and the data set has more than alpha squared n squared dimensions, and I get about 1 over alpha squared reference samples from the population, then the attacker can trace at least 1 over alpha squared people in the data set. So again, you can basically interpret this as saying that the only two things you can do to defeat tracing attacks are adding Gaussian noise or subsampling. Everything else succumbs in basically the same way. All right, so these are the results. I'm going to spend the rest of my time giving you some examples and a taste of what sorts of techniques go into proving these results. And then at the end, I'm going to give you a slightly different model that we're working on now where I think we can say some cool things. And I'm not going to talk about this highly quantified statement anymore. I'm basically just going to talk about the exact case, the first thing I told you about exact statistics, and the other extreme where you get, basically something so noisy that it's almost not an approximation to the mean anymore. So I want to go into some detail about this result. I'm going to talk about what sorts of things go into proving it. But the first thing I want to talk about is what is the attack. So I keep saying there's some attack, like there's some way to trace. And you may be thinking that it's like incredibly complex and it's some, very devious thing that an adversary could do if they were like very clever. But it's actually just about the simplest thing you could possibly imagine doing. In fact, the whole attack fits on one slide in a comically large font designed to emphasize the fact that it fits on one slide. So here's what the attack is. Like in words, the attack is you're going to basically ask, given this released mean, and given a random member of the population, or the mean of a random member of the population, and the target individual, I'm going to ask which of the following is true. So either the target individual's data is closer to the released statistics, or the random individual's data is closer to the released statistics. And if the target individual is significantly closer to the released statistics, then I'm going to conclude that those released statistics somehow depended on the target individual's data, which in my model can only happen if that individual was in the data set. By definition, if the target individual is out of the data set, then they're independent of the data set and they're independent of the statistics. Okay, so the whole attack is you get the target individual's data t, the noisy statistics q hat, and some reference information about the population z. You compute the inner product t dot q hat, and you compute the inner product z dot q hat. And if the difference between the two is significant, where I'm going to choose the significance threshold later, then you declare that the target individual is in the data set, and otherwise you declare that the target individual is out of the data set. Right, and this is, by the way, like a good time to make just a little point about sort of what are the semantics of the attack. So, when I say that I can determine if you're in and out of the data set, I don't mean that I can take like an arbitrary person and determine if they're in and out of the data set. It's really specific to the fact that I'm either looking at a random person from the data set or like a random person from the population. Okay, so if you just look at the structure of the attack, if I knew the population mean, then I know the directions in which the errors go. Like I know whether q hat is too high or too low. And it's extremely easy for me to come up with some target individual for which the attack would say yes. So you can think of it in sort of a forensic sense. Like if I wanted to frame someone for a crime, like it's fairly easy. And yet people show up on trial and you say, I have this evidence about this person. It seems, beyond a shadow of a doubt they committed the crime. It's not that I couldn't have planted the evidence. It's more of like, what were the odds that I chose to plant the evidence about this specific person? Okay, good. So we have our attack. I've stated the results. And before I give you a taste of the proof, let me just show you that this attack actually works. So, as a theoretician, I like to give statements involving big O's and hiding polylog factors. That's not going on here. Like, the attack totally works. So here's a very simple example. It's admittedly like a simulation. This is not an empirical study. But I didn't cherry pick this example. I mean, this sort of phenomenon is fairly robust. So what I did is I took uniform data. Like I just took a completely random matrix for my data set. I computed its mean q, so we're in the exact case. And now I plotted two things. Like I did this a whole bunch of times, and I plotted two things. So either I took a random person in the data set and I took t dot q, and now I plot the value of t dot q, and my histogram is this orange distribution. Or I took a person who's out of the data set. They just took a new independent random person and I plotted t dot q. And that's these blue histograms. And this is obviously too small to read, but I took a data set of size n and then different values of d. And here, d is 200. It's only twice as big as n. And you're already getting some noticeable separation between people who are in and out of the data set. And gradually it increases. Here's d equals 400. Here's d equals 800. And here's d equals 1600. And you can see that at this point there's very little overlap. I have really high confidence in determining whether a person is in or out of the data set. So again, this is not a real, in the wild field study, but this is just a demonstration that this works. It's a real attack. So this is for the exact case. What happens when you add noise? Like, I keep making this very bold statement that these attacks basically are matched by differential privacy. So let me show you what I mean. So here's the same experiment, except instead of the exact mean, I'm going to add Gaussian noise to the mean. So here I add no noise, so I get infinite differential privacy. I achieve no measure of differential privacy. And I do really well, because this is d equals 1600. I said we do really well for exact statistics. Now I added more and more noise. And over here in the lower right, I added enough noise that we achieve 2 differential privacy. And notice that 2 differential privacy is sort of weak. I mean, this is we really think you should achieve more than 2 differential privacy. And yet even with 2 differential privacy, you're really getting a separation between the two things. So, in some sense, and in fact, you can even show, so Guy said that Gaussian noise is sort of the canonical example for differential privacy. So if you basically plotted 2 Gaussians, and you asked sort of what would 2 Gaussians that are at, how far apart would I have to make 2 Gaussians to achieve 2 differential privacy, you would not be able to tell the difference between that plot and this plot. They are the same. Okay, so obviously this is just Gaussian noise. I've made claims that we work against any way you could possibly introduce noise. But in some sense, why would you want to? We're basically showing that you can get this amazingly strong notion differential privacy, and when you do, you prevent tracing attacks. And if you add any less noise than that, we're going to trace you. So I think this is a cool picture. I think this shows, at least gives an idea of the statement I'm making, that differential privacy is sort of tight. All right, so the analysis of these things is a little tricky. I wanted to show you pictures so you could see what actually happens without really grokking the analysis, but let me give you a taste of it. So let me start by showing what happens when there's no noise. All right, so this is the simplest model. You get the exact mean of the data set. I'm even going to make it simpler. I'm going to assume the data set is completely uniform. I'm just going to try to give you a taste of what happens. And basically, I want to establish 2 facts. So let's go back to this picture of what happens in my tracing attack when the dimension is 1600. And you can see that these 2 distributions for the in and out case are very far apart. But how far apart are they? So the answer is that the means I'm going to show are at distance about d over n. All right, so when d and n are comparable, the means are going to be about 1 apart. And the standard deviation is about root d over n. So again, when d is equal to n, the standard deviation is about a constant. And as I make d bigger, they're going to get further apart relative to the standard deviation, and I'm going to tell them apart. So let's see why that's true. So let's start by analyzing what happens when the target data is out of the data set. So in this case, you have a random target, a random data set, and the target is independent of the data set. So how would I analyze the distributions, the blue distribution of this inner product? Well, the target is a sample from my population P, so its mean is just the mean of the population, which I called little p. And in particular, if I fix the data set X, which also fixes the mean of the data set Q, then when I average over random targets, the expectation of T dot Q is equal to P dot Q. Okay, and remember, the attack, it computes the difference between T dot Q and P dot Q. So now what I'm saying is that the mean of this quantity in the attack is 0. Okay, good. Mean is 0. So I've established half of 1/2 of what I told you, is that the mean of the blue distribution is 0. But I also told you that we need to bound the standard deviation of the distribution. And we do that using the fact that I'm going to assume that the data is a product distribution. I'm going to assume that coordinates are independent. All right, this is a modeling assumption. It's a strong assumption. It's not literally satisfied in any case, but it doesn't need to literally be true. What really needs to be true is that there are a lot of independent dimensions, or somewhat independent dimensions. And if you make this assumption, then you can use concentration of measure to argue that with high probability, this statistic you're computing is going to be smaller than this quantity that's about square root of d over n. Okay, so that's the analysis of the blue distribution. Its mean is 0, its standard deviation is about square root d over n. Now let's look at what happens in the case where the target is in the data set. I apologize, it's getting a little mathy. But The gist is to reduce everything to what happens in a one-dimensional data set. So we're going to, even though I said that all of this happens because we had a really high-dimensional data set, I want to focus on a one-dimensional data set, and we're going to see that you can get a little bit of signal about whether a person's in the data set, and then we're going to just sort of blow it up across d dimensions and extract more signal. So when d is 1, we just have a single attribute. And in this case, what am I looking at? I'm just looking at the expectation of t times q minus p times q. There's no dot products anymore, they're just numbers. And it's really just a calculation. You can work out that the expectation of this statistic is actually just equal to 1 over n, so 1 over the number of people in the data set, times the variance of like a single person's data. And as long as my data set isn't too biased, that variance is going to be about 1 over n. So this says that I get a gap of 1 over n for a one-dimensional data set. And because my attack is linear, it's just the inner product, this means that I get a gap of about d over n for a d-dimensional data set. And then I'm just going to apply the same argument about concentration to say that the standard deviation is about square root of d over n. Okay, so this is the gist. There's really two parts of the analysis. You establish that this test statistic, on average, is much larger if the target is in the data set than if the target is out of the data set. And then you use some kind of concentration to argue that when d is large enough, you're very likely to have the test statistic be over this threshold t when the target is in the data set and under the threshold t when the target is out of the data set. Okay, so that's the main idea. And I should say that if you only are worried about analyzing Gaussian noise, if you're really only worried about seeing what happens when someone perturbs the data with Gaussian noise to achieve differential privacy, then pretty much this is all you need to analyze the attack in that case. So the actual difference in means changes, and the actual standard deviation changes, but the approach for how you decompose the analysis and what you look at really doesn't change. So good. So that's a decent approximation to what happens in the noiseless case. Let me give you just a tiny taste of what happens in the robust case, the case where you get very noisy statistics. So remember, we want to say that you get a very noisy mean q, and you get one reference sample from the population, and your goal is now to trace like one individual in the data set. So you're not even trying to trace everybody because we know that'll fail. So let me just say that the analysis in the case where the target is out of the data set really doesn't change much. It's the same idea. You argue that this test statistic has mean 0 and is reasonably well concentrated around its mean. The really tricky part, where we had to get our hands dirty with these techniques of Tardosh for fingerprinting codes and some extensions of them, is the case where the target is in the data set. And as I said, the first thing that goes wrong is that you can't even hope to trace everybody. So we can't actually show that the expected inner product of the target's data and the release statistics is large for every possible target. So what we're going to do is we're just going to show that it's large on average over targets. Okay, we're going to basically take the average of the test statistics and show that that's large. And to do it, we proved what I think is a really cool Fourier analytic lemma. So this is a lemma that's probably a little beyond the scope of this talk, but I want to give just like a interpretation of what it says. So basically, it says the following. So it says, let me choose the mean of the distribution at random. All right, so there's no longer a fixed mean. I'm choosing a random mean for the distribution. And now I'm sampling a data set from that distribution. So I'm sampling n IID draws from that distribution. I'm computing its mean. And then I'm allowing you to take some arbitrary function of the data that supposedly approximates the mean. And I claim that one of two things happens. So I basically claim that either the score, this test statistic is large on average, or the expected error that you introduce into the statistic is large, again, on average. I said an expectation. So we basically show a win-win. We basically show sort of a smooth trade-off between how much noise you're adding to the statistic and how well the statistic correlates with a random person in the data set. And really all I want to say is, so that, like, I don't have time to prove the lemma, but there are many questions that I'm interested in. There's many questions about getting sort of optimal attacks, extending to different types of data that really boil down to like these cool Fourier analytic statements. And so I think it's a really cool area to work on. I think there's a lot of deep math here, and we're just scratching the surface of it. All right, so let me spend a few more minutes just kind of going over some extensions. So I told you about just a little taste of the analysis, but I want to remind you that what we get is basically this very kind of smooth set of trade-offs between all of the different goals of the attacker. And so what we said is that if you get the target's data, some mean of the data set that you're promised is alpha accurate on average over coordinates, and the data set is alpha squared n squared dimensional. Oh, sorry, this should say 1 over alpha squared reference samples. Then the attacker can trace 1 over alpha squared individuals. And like I said, this basically means that there's one of two things you can do to defeat a tracing attack. You can sample some fraction of the data, about 1 over alpha squared people, or you can add Gaussian noise to achieve differential privacy. And other than that, we are going to get you. We are coming for you. OK, so that's tracing attacks. I showed you, a little taste of how this works in practice, a little taste of the analysis. And I hope mostly what I conveyed was just a sense of what types of attacks are possible when you're given a data release that contains no PII, has no possibility of re-identification, only has aggregate statistics. And remember, I wanted to give this interpretation that differential privacy achieves the limits imposed by these attacks. So differential privacy is not free. Privacy has a cost. As I said, these attacks work when you add much more noise than the sampling error already in your data. So these attacks do mean that privacy has a cost. But the positive spin on it is that we have this very nice privacy notion that will achieve privacy and has very little cost beyond what we just showed is necessary. And I sort of conjecture that this phenomenon is more pervasive. So we talked about just the case of the mean of the data set. Now, of course, many things you want to do imply computing the mean, either in a fairly obvious way or the types of techniques I showed you can be extended. So Kunal talked about the case of optimizing functions, solving the lasso program, for instance, or regressions where optimal lower bounds for differential privacy actually come out of these types of techniques. Principal component analysis is another case. What Aaron is going to talk about later on, an adaptive data analysis, we have some essentially optimal lower bounds that really come from kind of like souped up versions of these attacks. So even though the mean is very simple, in some sense that's a strength. Like the mean is the first thing you'd want to do. So of course, a lower bound for the mean is a fairly general object. But I want to talk about one setting that's not covered that we're working on now, which is variable selection problems. So, when you have a really high dimensional data set, potentially you don't even really want the mean of the whole data set. Like I say, oh, the mean is like the first thing you'd want with a data set. And it kind of is. But on the other hand, if you have like millions of dimensions, most of them are probably really irrelevant to your problem. Right? And this is sort of what you do in big data. Like you collect a lot of data, but you're really looking for something fairly small hiding within it. So what if instead of releasing the whole mean, I have a d-dimensional data set, but what I really do is I tell you the k most interesting statistics. And for today, like the most interesting, I'm just going to mean the most biased, like the entries where the mean is largest. Of course, there are other definitions of what it would mean for a variable to be interesting, but we got to pick something to start. All right, so you have this like short, fat data set, but now you release this like fairly skinny object, which is just the k most biased columns and their mean. All right, so I tell you which columns, and I tell you the mean of those columns. And maybe I also add some noise. So maybe I don't select the real top k columns. Maybe I throw in some extra columns. Maybe I drop some. Maybe I perturb the means. So the same idea, I add some noise to it. And let's see what happens in practice. So here, what I've done is, again, I've taken uniform data. I'm not adding noise. I'm just taking like the true top k statistics. N is 100, and I'm fixing k. So like you get 200 statistics. And we saw that if you get 200 statistics out of a real set of 200 statistics, that's really not like so good. Like you get some difference between in and out, but it's not like really conclusive. But then what I did is I like cranked up the dimension. So I said, really, These are the top 200 statistics out of like a bigger and bigger set of possible statistics. And you can see that for even like somewhat modest numbers in modern context, 6,400 dimensions is really not that much, you actually get really good resolution. You really get to distinguish between people in and out of the data set, even though you were only given like a fixed number of statistics, which on their own seems very small. So I think this is an important phenomenon, that just because you're releasing a fairly small amount of information, if the information you choose to release depends on what else was in the data set, it can still be very disclosive. So it's not enough to just throw out the boring parts of the data set, because of course which parts of the data set are interesting are the ones with all the good information about the people in the data set. So I think this is interesting, and from a theoretical perspective, we do know how to find these k interesting statistics without releasing all the statistics. So things like the exponential mechanism that Kunal talked about, or the sparse vector technique that I think he name-checked but didn't describe, basically say that if you want the k largest entries of a d-dimensional data set, and you want error vanishing relative to the sampling error, then you need n to be bigger than about k log d, right? So remember, if you weren't selecting these, if these were the only k statistics in the world, you would only need n to be bigger than about k. But you need to pay this log factor in the dimension. And in some subsequent work, we've been showing that that's tight. And I should say, just to embarrass her, this is subsequent work with Mitali Bafna, who's sitting over there. She is applying to grad schools near you as we speak. And she is extremely talented. So yeah, I recommend you admit her, whether you like this work or not. Looking at you, people at Princeton. Mitali, are you sufficiently embarrassed yet? OK, right. Anyway, so what we showed is that basically this algorithm is tight, at least in the parameter regime where you want the noise to be vanishing relative to the sampling error. So pretty much the same attack model, we showed that this picture is fairly robust. So we basically proved that this is the real story and that it's a fairly general phenomenon. And I think this holds up in many other settings. So we're also looking at release of contingency tables, regression models, and I think this is a very general phenomenon that people should be aware of when they're implementing differentially private algorithms and when they're doing theory of differential privacy. So I'm happy to just wrap up now, leave some time for questions. So the summary of what I talked about is that individual data leaves some kind of fingerprint even in these aggregated statistics. So even in a big data set where I just aggregate some statistics, every statistic seems to have very little information about any one individual. Surprisingly, you can still use this information to detect the presence of that individual in the data set. You can trace that individual back to the data set. Right, and this is basically a general paradigm for what it means to attack a sensitive data set, even in settings where re-identification just doesn't apply. Okay, this is sort of in some sense, a canonical paradigm for attacking aggregated statistics. And then more specifically, I talked about these robust tracing attacks, where instead of just showing that tracing is possible, we can actually show that tracing will succeed sort of right up to what you can do for differential privacy. So this is both limits of differential privacy, but really it's just sort of limits of privacy in general. I hope I gave you at least enough of a taste to convince you that there are some cool mathematical problems involved in this line of work. And I'll just leave you with this sentiment, and then thank you.